Our goal for today, and actually the next few lectures, as I mentioned last time, is to try and give you a pretty broad overview of how the internet works. And as I mentioned again last time, people tend to, or textbooks even, tend to do this one of two ways. Either they go top-down, meaning they start with this is the internet as a whole, let's start looking at what's inside it, or they go bottom-up, which is they say, here's a link, I'm going to get data across a link, and build up from that to the internet. We're going to do it both ways. So this lecture, we're going to start bottom-up. So we're going to start very low level with individual links and bits flowing across the link. So goal for today is to cover 4 topics. The first is we're going to look at how is data organized or transferred across the internet. Okay? Then we're going to get to what is really a very, very fundamental question, almost even before you start building a network, which is how are we going to share network resources? So how are we going to share in terms of users, in terms of applications, in terms of bits on the wire, and so on. And along the way, as we're going through this, we're going to start to understand what we call the life of a packet. We haven't yet talked in lecture about what a packet is. I think your TAs gave you a preview and discussed it as the life of data as it flows through the network. Okay? And in that way, along the way, we're also going to identify what the core topics that we're going to cover this semester are, okay, that we're going to do a deep dive on as we go along. And so with that, let's start with this picture that we had from the last lecture about what internet infrastructure looks like. And as I said, there are 3 main components. We have end hosts, we have switches, and they're all interconnected by links. And we also said that the internet really has just one basic task that it performs, and that's to transfer data between end hosts. Okay? And so we had this picture where we said we have data here, we have a path, data flows along that path. Can I ask you, please? Okay, so at the beginning for this lecture, we're actually going to ignore this entire big picture, and we're going to hone in here on this one teeny tiny piece of this picture. And that piece is we have an end host, it's connected by a link to a switch, and we want to transfer some data across this one link. And we're going to start with, again, we said data, that we're running applications on the internet, and applications have data. So let's say that in this context, we have this image, and the end host wants to send this image over the internet. So very basically, the first thing it's going to do is it's going to construct what we call a packet. And a packet is a unit of data that gets transferred across the internet. And maybe what we're going to do is take actually just a portion of that image and put those bits that represent that image into this packet. Why a portion? I'll get to that in just a minute. But for now, think of it as I'm going to take some chunk of that image, and now I have a bag of bits that I'm calling a packet. If I were to send this out into the network, what is the switch supposed to do with this? Right? It's just a bag of bits. It represents an image. The switch doesn't actually know what to do with that. And so we get to what is actually, especially for us in this class, the most crucial part of a packet, which is we're going to have this little additional portion that we add to every packet where we're going to put metadata in. This is any information that tells the switch or tells the network how to handle this bag of bits, how to handle this packet. Okay, and we call that a header. And we're going to talk at length in this class about headers and what goes into it. And why is it so important? This header, you can think of it as it carries the instructions that tell a switch what to do with a packet. So it's the set of instructions that the end host uses to tell the network, to tell switches what to do with a packet. And it's also the set of instructions that a switch will then use to tell other switches what to do with a packet. So to repeat that, when a switch receives a packet, it's going to look at the header in order to know what it has to do with this packet. And it's also going to use the header to tell another switch what it should go on and do with this packet. Right? So when you write code in general, you tend to think a lot about APIs. Right? And we've all heard a lot about the value of a good API, what parameters go into the API, and so on, and how crucial it is to actually writing a good function. Before you write the details of the function, you actually often write the API, and you circulate it and ask people, is this a good API? You can think of the header in some sense as the API to the network. Right? It's even more crucial than in your software because this is an end host telling a switch. They're 2 different entities built by 2 different parties, what it should do with that packet. And it's also much more crucial because this function is implemented by the internet at large, by all the switches in the internet. So that's why we obsess so much about headers. The rest of the packet, those bits that came from that image, we're going to call a payload. By and large, the payload is really application data. It's data that the network typically doesn't really care about. It doesn't need to understand it. It's just what one end host wants to send to the other end host. The end hosts care about it, but the switches don't have to. And that's actually part of where the generality of the internet comes from, the fact that you don't care about what application data is in the packet. So one other point I should tell you is that typically packets are not all the same size, but there is typically an upper limit on how big a packet can be. That upper limit tends to come from a variety of different reasons, but typically because of the particular link technology that you used. So the most common one is Ethernet. And Ethernet has what we call a max size, and we'll talk about this at length when we talk about Ethernet, but has a max size of 1,500 bytes. And this is why if you go looking at packets on the internet, there's a large number of packets that are 1,500 bytes. But Wi-Fi has its own upper limit on how big a packet can be. Fiber technologies have their own upper limit. And some of this is also historical. The reasons why Ethernet had 1,500 bytes doesn't quite apply anymore, but we're still just used to, it's worked out well, and we're used to using it. Okay, so not all packets are going to be the same size, but they can't be as large as you want them. There is a cap, and that's why I had to take a portion of the image and put it in one packet. Okay? Will all packets be the max size? What do you think? So I said Ethernet will allow you to send 1,500 byte packets. Someone's shaking their head. Yep. Right. So if the size of the image doesn't divide by 1,500, I'm going to have some leftover bytes. I'm going to send them along. Any other reason why I might have fewer than 1,500 bytes in a packet? Balancing load in terms of how much load you put. Interesting. Yeah, that seems plausible. Why not? Yep. The header will take some bits, so that's right. When I say packet size, I'm actually usually referring to the sum of the header and the payload. So what I can put into the payload is the maximum minus the header, but very good point. Thank you for clarifying that. Any other thoughts? Yep. Good point. Hold on to that thought because we'll get to that in a couple of lectures, but your point is correct, which is that there might be things other than pure application data that you wanted to send. You might have wanted to send, for example, a checksum over the image to show that the bits were not corrupted or something to authenticate the data and so on. So yes, when I say application data at this point, you can think of it almost as anything the application wants to send. It doesn't literally have to be those bits in that image. Any other reason? These are all good reasons, yep. Yeah, absolutely. So the point raised here was I might just not have that much to send, right? If I'm just saying, yes, I got the data, maybe that's like 30 bytes, 40 bytes. So I just want to send that data. Because what would have been the alternative? The alternative would have been to say, I can send 1,500 bytes. I'm going to wait until I have 1,500 bytes worth of data to send. And that's slowing the application, and I might never have that many bytes. Or in something like an audio communication, I have a small number of bytes to send. I really don't want to delay it. So I want that flexibility of sending fewer bytes in a packet. Yeah. So just to recap, packets are, you can think of it as a chunk of bits. It's made up at a high level of two big pieces, payload and the header. The payload is meaningful only to the endpoints. Okay. It could be bits from a file, video, whatever the application wants to send. The header, on the other hand, is meaningful to both the network and the endpoints. Okay. So now let's start to think about what should go into the header. What do you think is the most important piece of information that has to go into the header? Yep. The location you're sending the packet to. Can I call that a destination address? Yes, absolutely. Anything else? I would say that is the most crucial piece of information you have to get right and you have to get into the header. What else might you want to send in the header? Yep. Time to live, Simo. What is? You're right. Right. Very good point. Let me try to, we're going to get to that many lectures from now. But the idea is that let's say your packet was having trouble going through the network, that maybe it was going around in circles and the switches were confused about how to forward it. You don't want that packet to circle and loop in the network forever. So there's this idea of a time to live that will kind of say, this packet has been in the network long enough, I'm just going to throw it out. Something's wrong with it. Anything else? Yep. So the source of the packet, what do people think? Do we have to have that? For example, do we have to have the time to live as well? That's completely true. I'm just trying to unpack the decision a little bit. Do we need the source address? Thoughts? Okay, so the answer is yes, because how else does the source know how to respond? Any other thoughts? Anyone disagrees? Yep. Yeah, so the thought was, well, we don't strictly need it because if the end host is the one that needed the source address, I could have put it in the payload because remember, the destination is going to look at the payload. So the network did not need to know the source. Yep. Aha, nice one to catch. Okay, so if we don't think about TTLs or error conditions, then I would say you're kind of both right in the sense that it is convenient to put the source address in the header because most communication tends to, you send a piece of data, then you have a response, so isn't it convenient to have the source address there? Right? It's what you would expect all communication needs. Let's put it in the header. That's absolutely true. It's about convenience. So the person that said, well, it wasn't strictly required because I could have put it in the payload and that way the destination would have known how to send the response back. It's also correct. So if we were saying that's a strict requirement, no, it's not a strict requirement that you have a source address. But then we had yet someone else that said, well, actually, if I combine what somebody said before, which was this packet has been in the network too long, and I say that I want to send an error message back to the source so that it knows, which is not necessarily what the internet does, then I would want, the network would want or would need to know what the source address was. So if ever the network sends a signal or an error back to the source, then I'm going to need a source address in the header. So that's actually a strict requirement then again. Okay, so I'm walking you through all these things not to make it sound complicated, but to make you realize how even a decision like, do I need a source address? You have to think through why you need it. And is it required? Is it convenient? Why are you putting it in? And so on. So we do have, for the most part, source addresses in the header. Is there any other reason you can think of that's not come up? Yep. We're changing fields now. Protocol type, yes. Fair enough. I'm going to skip explaining that in the interest of time. We'll get to protocol types down the line. So this would be to tell the network, this is the type of protocol I'm running. Is it IPv4? Is it IPv6? So I am actually explaining it. And it is useful because if we say that a protocol has to evolve, it's kind of like a version number, right? You have to know which version are you dealing with or what protocol are you dealing with. So having a protocol type would be useful as well, and we do have that. Okay, I think I've covered this at length at this point. So we absolutely need the destination address. No doubt about that one. In practice, a few simplifications that we'll start getting into later in later sections. Most packets will typically have multiple headers, not just one. But for today's lecture, let's just assume there's one header and there's payload. And another concept that comes up repeatedly and is very useful to know is this notion of a flow between two endpoints. Because just as you saw that there was actually an entire image to send, and I only got to pack a portion of it into one packet. So in reality, there's going to be a stream of packets that are kind of all related in the sense that they're all part of the same communication between the source and the destination. And so we use the term flow to refer to this stream of packets. Okay. With that, let's get to now actually putting that packet on a link and what's involved there. And so from now on going forward, we started with this application data, but I'm only going to be talking about packets. And I hope in your heads you understand the connection between application data and packets. And if you don't, then stop me now. But so now let's get into, we have a packet. It has an address. For now, I'm going to say its address is UCB. That's not what actual internet addresses look like, but let's say it is. And then there's some set of bits that we're not going to care about. This is a good time actually to talk a little bit about a link. Let's look at what goes into a link. And typically a link is characterized by 3 properties that capture the performance of that link. Okay? The first is this term you've all heard about, bandwidth. Right? We all say I have a gigabit per second, 5G is going to give me whatever, 5 gigabits per second. No, that's not true. But we talk about network speeds in terms of bandwidth. It's how many bits per second you're hoping to get out of a link. So the bandwidth is really the number of bits per second that you can put onto the link. If you think of it, the analogy I like to think of is a pipe, and you're putting water into the pipe. And so your bandwidth is like the width of that pipe. It's how quickly can you put water into that pipe. The wider it is, the faster you can put water into it. It's exactly the same with a network link. The higher the bandwidth, the faster you can put bits onto that link. The second metric we talk about is the propagation delay. This is the time it takes for one bit of information to travel along the link, to go from the beginning of the link to the end of the link. Again, going back to our analogy of a water pipe, if I put a drop of water into the pipe, at what time did it come out on the other end of the pipe? Okay, so this is dictated by physics. It's just how long does it take a bit of information to flow on a pipe. And then lastly, so you can think of that again as the length of the link. And then the last property is just the multiplication of those two. It's what we call the bandwidth delay product. It's you take that bandwidth and you multiply it by the propagation delay, and that gives you your bandwidth delay product. We use the term BDP often to talk about this. And when we get to congestion control or sharing network resources, these concepts and BDP in particular is important. What does the BDP signify? The BDP, you can think of it as the capacity of that link. Right, so again, going back to our analogy of a water pipe, if I did not take any water out of the pipe, if I blocked it at one end and I filled water, how much water could I put into that pipe? That's the BDP, or the capacity of the link. Right. So if I cut the link on the two ends, and I looked at that link, and I could see how many bits I could pack onto that link, how much information is actually on that link, that's the BDP. Okay? So these three properties, really critical that you fully internalize what these mean, because they have a lot to do with reliability, delay calculations, congestion control when we get to that later in the lecture. And so let's actually walk through one packet going across one link in the context of these properties. So let's say I have a 100-byte packet, so 800 bits, and my link is a megabit per second and 1 millisecond. One way that we're going to use to understand performance and networking protocols in general is with the help of these kinds of timing diagrams. So what I'm going to show you here is time going down. Right? Time is moving down as I go down the timeline. And I'm going to show you the events that are taking place at the end host and the switch as we go down in time. So let's say as I'm sending this 100-byte packet, at time 0, let's think about that very first bit of information we're putting on the link. Right? I said my link has a bandwidth of 1 megabit per second. That means I can put 1 million bits in 1 second. I can put 1 million bits onto the wire. That means that to send 1 bit, it takes me 1 over 1 million, or 1 microsecond. So after 1 microsecond, I have that 1 bit on the wire. That bit is then going to travel across that link. The time it's going to take to go across that link is the propagation delay. So that's 1 millisecond. So at 1 millisecond plus that 1 microsecond, that first bit has arrived at the switch. Okay? I had 800 bits to send, so it's going to take 800 times 1 microsecond. So at the end of 800 microseconds, I would have sent all of my 800 bits. This is the point at which I can say that the end host has finished transmitting the packet. That 800th bit is then going to travel across that link. It's going to take that 1 millisecond. And so the last bit is going to reach B at that 800 microseconds plus 1 millisecond. This is the point that 1.8 milliseconds is the point in time where I can say that the switch has received the packet. It has received all the bits in that packet. So that gives us this calculation where we say the packet delay is the transmission delay. That's the time to put the bits in the packet on the wire, plus the propagation delay, which is the time for those bits to travel across the wire. And the transmission delay, in turn, is the packet size divided by the link bandwidth. Okay, so this is my delay across a single link. As we go in the semester, we're going to start talking about delays that packets experience as you go across a series of links. But it all builds on this. Any questions? Yeah, how do the bits actually get onto the link and how do they get transmitted? This is really the EE physical layer side of a link. Right? Different links have different technologies. For example, a fiber link, it has a laser on it that is doing whatever lasers do to convey that light through the link. Right? Wi-Fi, you have different types of signals. Ethernet has different signals. We're not covering those in this class, yeah? Yeah, this is again actually a physical layer question. Different, if you actually dug into how a particular link works, different links have slightly different ways of doing this. Some of them will take 4 bits and encode it slightly differently and then send out 4 bits in parallel. Others, it really is a serial link where it's 1 bit at a time. We tend to abstract that away for this class and we just say this is your bandwidth, which is, for your purposes, you can think of it as 1 million bits per second without worrying about exactly how those bits got on. Any other questions? So you'll be doing a lot of these calculations during sections, so don't worry about the exact math of it. But I do want you to understand how these parameters for a link matter. Okay? So here's a question. Let's say I give you 2 links. You get to choose which of these 2 links you get in your house. For example, let's say your ISP is offering you these 2 link options. One of them has a bandwidth of 10 megabits per second and a propagation delay of 10 milliseconds. The other has 1 megabit per second and the delay is 1 millisecond. So it's 10 times lower in bandwidth, but it's 10 times faster in terms of the propagation delay. Which one do you think you want? Take 10 seconds to think about it and then we can discuss. Thoughts? Which? Yep. Okay, so we have someone here who likes link 2 better. Anyone disagree or agree or want to add to that? Depends, say more?
So link 2 would be better for a device that you want things all the time, not necessarily care about the data. But link 1 would be something like a more consumer. Link 1 would be a television because you won't see it live, but at least you'll see more data.
Right, absolutely right. So the answer is it depends. So you were also right, but the answer is still it depends. So it depends on what workload you had in mind. So let's take an actual example to see that. Let's say that I had a computer, let's compute the packet delay for a 10-byte packet. Okay, that's the analogy to the doorbell that you had in your answer. So if I had a 10-byte packet to send, and if you redid the math, what you would see is that with link 1, it took you 10 milliseconds for exactly the reason you described, which is I only have 10 bytes to send it. It's not a lot of bits. And so my transmission delay is not that high. But then the time for those bits to travel across the wire dominates. And so in this case, link 1, which had a high propagation delay, does worse than link 2, where that time for those small number of bits to travel was just 1 millisecond. Right? So in this case, link 2 is looking better. On the other hand, if I said I have 10 kilobytes, 10,000 bytes to send across that wire, right? And if you redo the calculation, now actually link 1 is looking much better because I have 80,000 bits to put on the wire. And so my bandwidth starts to matter. My bandwidth is, remember, how quickly can I put those bits on the wire? And so if I only had a megabit per second, I'm taking a long time to put those 80,000 bits on the wire. And yes, then they travel, but the dominant factor is the time it took me to actually transmit those bits. This is why sometimes when you're on a Zoom call and things are breaking up, you turn your video off. In that case, if you'd had a better, higher bandwidth connection at home, that would have helped you. That which video consumes a large amount of bandwidth, then your performance would have been better. On the other hand, if you're on an audio call with someone that's across the globe, and you can hear a delay, that you say something to them and then clearly they hear it after some amount of time, that communication, the reason it's not doing so well is because of the propagation delay. So you could go to your ISP and upgrade your link, it's not going to help you. It's just the delay that it's taking across the internet for those bytes to go. That's what's causing you that effect. So both matter, and what it matters on is how much data you're sending. I want to give you one other way of looking at packets on a link. So far we've been talking about these timing diagrams. Right? The timing diagrams are useful for you to understand the events happening at the two ends of a link. It tells you what the different entities in the network, when they're seeing different events. A different way to look at it is to look at it from the link's perspective. Okay? So remember, we're going back to our picture of the link as a pipe. The width of the link is the bandwidth. The length is the propagation delay, and the capacity is the bandwidth delay product. I could take exactly this picture on the left and represent it in the one on the right. Here it's showing you packets occupying that link. And where on the left I had the packet transmission time, this was the time it took at the end host to put the bits on the wire. That time now turns up as the width, what portion of the link is that packet occupying. That is your transmission time. When do you think we're going to use the figure on the right? When is it useful? Yep. How are you sharing resources, right? From the picture on the left, it's a little harder to get an impression of how busy is your link. When you look at the one on the right, they actually tell you the same thing, so it's not that there's information in one that's missing in the other. But when you look at the one on the right and you see a large number of different links, the leftover space on that pipe immediately tells me how much capacity I have left over. So it's visually a very easy way to get it, I think. So both useful ways of looking at packets traveling through a network, and we're going to use both ways as we go through the semester. Any other questions before I move on? Actually, I had one little question, but let's pause for questions after this question. So here's another exercise for you. Here's my link. It's 1 megabit per second, 10 milliseconds. As the propagation delay. I want you to think about just, in your head or doodle, what would this picture look like if I said that my link is 1 megabit per second, but now has a propagation delay of 5 milliseconds? And then also think about what this picture would look like if I told you you have 10 megabits per second, so 10 times the bandwidth, but your propagation delay is 1 millisecond. Okay, thoughts? What should the one on the left look like? 1 megabit per second and a propagation delay of 5 milliseconds? Yep. Pipe should be half as short, exactly. Does this make sense to anyone? Does anyone want me to explain this? All I've done is shrink the propagation delay. What about the one on the right? What should that one look like? Yep. So this is not to scale, obviously, but it should be 10 times as wide. And because I could send packets so quickly onto the pipe, each packet has become very skinny when I look at it on the pipe. Right? It's kind of stretched out because it didn't take me much time to transmit it. And that's why these packets are narrow and tall and skinny. Okay, so to recap, packets on a link, we have this packet, has a header and a payload. And we now know how this packet is going to make its way across that link and arrive at the switch. Okay. So now think a little bit. What are we going to do at that switch? So remember, a switch is defined by having a number of interconnecting links. So it locally has a number of links that connect it to other switches or end hosts. Okay. So when the packet arrives at the switch, what is the problem that the switch has to solve? Right. So the packet, it looks at the header and it says, this packet is going to UCB. UCB is somewhere on the internet, somewhere in this network. Some of its neighboring switches are going to take it towards Berkeley. Right? Others are not. So what the switch has to know is which of its links, and I'm going to number them here for convenience, is going to take this packet towards Berkeley. The switch doesn't really need to know exactly where Berkeley is. All it needs to know is, at this point, with this packet, which link should I forward it, send it out on. And in order to do that, the way we're going to do that is that every switch stores what we call a forwarding table. This is just a table that for now we're going to say all it has in that table is a destination. And corresponding to every destination, which of my local links or my immediate links is going to take me towards that destination. Okay, so now this packet arrived. I took out, the switch takes out UCB, looks it up in the table, and says, aha, link number 2. I'm going to send the packet on to link number 2. And then the next switch is going to do the same thing. So this is what we call a forwarding table, and what the switch has just done, we call this operation forwarding a packet. So switches forward packets. Okay? That's what the per packet task that a switch does is. So to recap, let's start to build that life of a packet now that we understand a little bit more. Life of a packet, the source has some destination data that it wants to send a destination. It chunks it up into packets. Each packet has a payload and a header. The packet travels along a link. It arrives at a switch. The switch looks up the destination in its forwarding table and forwards the packet to what we call the next hop. Okay? So it sends it out over one of its links. And then I'm going to repeat these last 2 steps until the packet reaches the destination. Okay? So this is kind of life of a packet as a starting point. You now understand how a packet goes from point A to point B. Let's think about what are some of the fundamental challenges in this. So, I put this picture up and I said we have this packet, we have this forwarding table and so on. I glossed over a large number of details when I put this picture up. Anyone want to speculate on what some of the challenges are? Yep. Right. So how would this scale? Am I really going to have a table that has an entry for every single destination? So how do I scale this forwarding table? Yep. Anything else? Yeah? You might have 2 parts to the same destination. Fancy, but you're right, absolutely. That's something we call load balancing. We'll get into later. So what if I wanted to have more than just one link that I could use to send that destination to at the back? What happens if you lose data? Yeah, let me turn that around a little bit to say, when do I lose data? Or what would cause me to lose data in this context? Yep, you were next, I think. Right, so what happens when a link goes down? Is my forwarding table, I had a forwarding table that said go out over link 2, but maybe link 2 is actually down. What should I do? So how do I make this resilient? Yep. Exactly. Where did this table come from? I just magically said I have a forwarding table. How did I get it? And importantly, how do I maintain it as links come and go? Yep. I'm looking for one more. Yeah? Loops as I was forwarding. How do I know that my forwarding, these rules actually take me to the destination? Yes. Valid, not the one I was looking for, but still correct. Okay, the one I was looking for was, where did this address come from? Okay. How did the source know what address to use for Berkeley? And kind of cheated in the sense I said Berkeley, so you can imagine that sources know where they want to send their packets. But in practice, we know we're not going to actually have Berkeley as a destination address. So where did this address come from? What does it actually look like? How do end hosts discover the addresses of other end hosts that they want to talk to and so on? And then just a whole host of information of challenges around this question of this forwarding table. And many of you brought it up. Where did it come from in the first place? How did we calculate it? How do we know it's correct? How do we maintain it as links go up and down? How do we make it scalable? How do we make it secure? And so on. Those are some of the key problems we're going to be studying in the next few weeks. So the first is addressing and naming. So in the real world, we all have names and we have addresses. Like my name is Sylvia. My office address is 413 Soda Hall. When let's say I move my office to now sit in Corey Hall, my name stays the same, but my address changes. Okay? And in the real world, we you don't want to refer to me as the person that sits in 413 Soda Hall. Right? You would rather talk to me about me as Sylvia. And so in the real world, we have names and addresses, and exactly the same way on the internet, hosts have network addresses. This is where on the internet topology is a this host? Where can I find this host on the internet? And separate from that, that host will also have a name, which is what is this host? So for example, when I say I want to talk to google.com, that means a server whose name is google.com. But that server lives somewhere on the internet topology. That is its address. And so we need a naming and addressing scheme that works at internet scale. Because remember, on the internet, you can reach any host. So unlike the real world where nobody outside a very small set of people know what my address is, on the internet, in principle, we want to be able to reach any host on the internet. So how do we discover their names? How do we discover their addresses? How do we keep that up to date? And so on. So IP addressing is the topic that's going to cover this. It'll be in a few lectures from now. A related one, though, is mapping names to addresses. So think about this when you access a web page, let's say CNN.com. What you really want when you're going to a browser and typing that out is you want to access the content that's being served or stored at a server that's associated with CNN. So really what you want to do there is you want to take this user level name, that's CNN.com, but the network doesn't understand these names. It doesn't know anything about CNN. So you want a way of taking that name and translating it to a network address, which is going to be an IP address. And we'll talk about what IP addresses are. And so what you want is a system or a solution that allows you to map or resolve names to addresses. That system is going to be something we call the DNS, or the domain name system, that does that translation for us. Not as easy as it sounds again, because servers come up or down. As someone like CNN maybe wants to have 10,000 servers, not just one, and it wants to load balance sources across all of those. So this gets pretty complicated as well. So in a later lecture, we'll talk about DNS. That's actually in the second half of the semester. The other challenge that came up was this question of the forwarding table and routing. So in general, when a packet arrives at a router, the forwarding table is going to tell you which outgoing link that packet is going to be sent out on. Getting to that forwarding table is the problem of a routing problem. Like, how do you compute that forwarding table that's necessary to deliver packets? This topic of how do you do routing, we're going to spend many, many lectures on this. Okay, at least 3 or 4 for basic routing. You're going to do a project on it. And then we're going to do interdomain or more complicated routing later. So I want you to have just conceptually in your head what routing involves so that you start to build that picture. And so conceptually, we've been talking about network topologies, and you can look at the figure I have on the slide, and you can just visually, you can figure out a path. Right? What are we actually doing when we talk about these switches and links and end hosts? What we're showing you is a topology, how they're interconnected, or in different words, a graph. Right? This should be very familiar to all of us. It's a graph. It's a graph where switches and end hosts are nodes, and links are edges. And we want to compute paths over that graph. We all know lots of graph algorithms from Dijkstra's to Bellman-Ford, different ways of computing paths over graphs. That's really what routing is, except that this is now a distributed routing algorithm that's going to run at an internet scale, and it's going to be run in a decentralized, distributed fashion across all the switches and routers. But you can actually conceptually think of it as, I have a routing algorithm that's running at all the switches in the internet. And what that algorithm is going to do is it's going to learn what this topology or that graph looks like. And then it's going to pick paths through this topology. And so the output of that routing algorithm is going to be a set of rules that say something like, if the packet is going to destination X, use this link. If the packet is going to destination Y, use this other link. And every router is going to do this individually. Okay. And so the output of running that routing algorithm is that every router is going to have this forwarding table that tells this router, for each destination, which of your local links you should forward the packet on. Okay? This is the forwarding table. So the output of computing, running that routing algorithm, is this forwarding table. Any questions here? Yep. Yes, for now, let's just say that that is our mental picture. That for every let's forget about the practical problems of storing a table that's so large it has every destination on the internet. Let's say that that's what we're going to do. We're going to learn the entire topology of the internet. We're going to compute this giant forwarding table, and each router is going to store this forwarding table. Clearly, this is not a workable solution, but it's a good enough mental picture for now. Any other questions? Right. So in this process that I just described, where a router learns the topology, picks paths, and then computes a forwarding table, the router is actually doing two different tasks, and the distinction between those two is actually very important. If you think about it, it's figuring out how to compute that forwarding table, and then it's actually using that forwarding table to process packets, to forward packets. And we call the difference between this computing the forwarding table and using the forwarding table the distinction between the control plane and the data plane of what a router implements. Here's a real-world analogy. You all have a driving license. Right? How did you get that license? There's an entire process for this. You probably went to the DMV. You filled out a bunch of forms. You showed what age you were. You gave them your social security number. When you were done with all of that, you got your driver's license. And now you use it all the time. Right? You get on a flight, you show it. You want to get your CAL ID, maybe you show your driver's license. So there's obtaining that license, and then there's using it. And if you think about it, they're completely different processes for how you went about doing those two problems. The people that issue at the DMV that issue your driver's license have nothing in common, or they operate independently from the people that are checking your driver's license at an airport. You probably go get your driver's license once in 10 years. It's a painful process, but you do it, you get it over with. You don't have to do it again for 10 years. You then use it almost every day. You use it frequently. So it's kind of the same in the control plane versus data plane distinction in the networking context, or what a router does. So control plane is the mechanisms we use to actually compute that forwarding table. It is inherently a global process, and so it's inherently a somewhat complex process. What I mean by that is, if you're a router in the middle of a network, what is your local state? What is the information you have locally without doing any additional work? You know what links you have, and you know what switches are next to you. Okay. In order to know which of those links to use to get to Berkeley, which is somewhere at the other end of the internet, I fundamentally had to know something about what the overall topology looked like, what other destinations are in the network. So it was kind of a global view of the network. Okay, so the control plane, this process of computing a forwarding table, inherently requires some amount of global information. Right? And so this routing algorithm that we're going to be discussing is part of the control plane. This process of what algorithm do I run across routers to compute that forwarding table. How often do you think I need to do this as a router? What's the time scale at which you rerun these routing algorithms? So let's say I discovered the topology, I picked paths, I compiled down, I distilled my forwarding table. When am I going to have to update it? Yeah? Whenever something changes in the topology, like what? You right? Just to expand on that. So if a link is added, or a link is removed, or a link fails. Anything else? If an address changes, right? It's another one. So basically the time scale is per network event. Right? And on a topology, the scale of the internet, we do have a lot of links going up and down, but it's not a million per second. So it's not once a year or once in 10 years going to the DMV, but it's not also, you have to do this every, a million times every second, you have to recompute your forwarding table. By network time scale, it's relatively infrequent. The data plane, on the other hand, this is now the using the forwarding table. Right? What is actually involved here, this is, again, inherently local in contrast to the control plane. Because the routing algorithm has already told me this is your forwarding table. My job on the data plane is just I take a packet, look it up in the forwarding table, send the packet on. Okay. I don't have to know where Berkeley is or has Berkeley crashed at this point in time. I'm just using that forwarding table. So the forwarding mechanisms, or what we're going to call IP forwarding, is part of the data plane. Yeah, question? Right. So good question. I should have clarified this earlier. The picture you should have here is that every switch holds a forwarding table that it has computed. Okay. Every switch or every router. So I'm using the word switch and router interchangeably. this came up in, I think, lecture 1. We use switch and router interchangeably, so they mean the same thing. It's the nodes inside your network that are helping end hosts communicate, forwarding packets across. Right. So does your home router have a forwarding table? What do you think? So I see a bunch of people nodding. Yes, your home router does have a forwarding table, and your home router has to know how to reach every destination on the internet. That forwarding table, when we get to it, doesn't have to have, it's not going to be this giant forwarding table with, an entry for every destination. We can collapse it down. And the reason, this is just a small preview, we'll get to it when we talk about routing. The reason it can is because your home router has only one way of connecting to the internet. So its forwarding table is essentially a highly redundant thing that says no matter what destination you're going to go off this link. So there's a default route that really is what saves our home routers. But in principle, yes. Good question. So how is, I have this mental picture. We have all of these switches. Each one is participating and running this routing algorithm independently and then is computing its forwarding table. How do I learn when something has changed in the topology and I have to change my forwarding table? That's what we're going to study in a few lectures. That's what makes routing hard. So good question. Hold on to it for a few more lectures. What is the time scale at which the data plane operates? So we said the control plane operates at the time scale of network events, when links go up or links go down. When is the data plane taking action? How often am I using or invoking or doing a lookup on this forwarding table? Anytime you send data, yeah. So can I say per packet? Every time I receive a packet, the switch has to look up the forwarding table. Okay, so very, very different time scales. It's per packet. Every time I receive a packet, I need to exercise the data plane. So control plane challenges computing routes at scale as links go up and down and the topology changes. This is going to be the topic we study when we talk about routing algorithms. How do we have these highly dynamic, scalable routing algorithms? Something I've not actually even brought up here is we have to do that while respecting ISP autonomy. So if you remember from last lecture, we said the internet is comprised of a large number of ISPs. They act independently. Each ISP is going to want to make its own routing decisions, and it's not going to want to communicate that to other ISPs. And so we somehow have to respect the autonomy of ISPs while making sure we actually have a path across ISP domains. This is going to be a topic that is a protocol called BGP, and we're going to study that later in the semester. Okay, so it's adding additional sophistication to routing. On the data plane, what do you think is the biggest challenge? So we said on the control plane, it's learning all of this global topology, coordinating it, yeah? Data loss, corruption, okay. Hold on to that one. That's not sure I would have said it's the biggest challenge, but yes, it is a challenge. How do we make sure the data is not getting corrupted on the wire? That's actually, if you ask the EE folks, they'll say that's the biggest challenge. Yep. It's all about performance. So the data plane, the biggest concern is performance. Let me give you an example to explain why. Let's say I had a terabit per second link. Okay, so that's 10 to the 12 bits per second coming in off the wire. This is a very standard link speed these days if you go look in the middle of the internet somewhere. And let's say I have 10 kilobit packets. This is again a pretty standard packet size. What this means if you do the calculation is that you have a new packet coming in every 10 nanoseconds. Right, so every 10 nanoseconds you have to read the packet off the wire, parse it so that you can find the address in the packet. Then you have to look up the address in the forwarding table, do whatever other updating of the packet header that you might want to do. And then any counters you have internally within the router, if, for example, you're counting how much traffic you've been forwarding. So basically any bookkeeping you want to do. And then you have to send the packet on that link. All of this in 10 nanoseconds. And this is an incredibly difficult engineering problem. As a fun exercise, try writing a little piece of code on your laptop that receives a packet and just sends it back out. We call it an echo server. All it's doing is read a packet, send it out. And try to time how long it takes. If you can get to even 100 microseconds, you deserve an award. It's actually extremely hard to write very low latency processing. And so this is what we'll talk about. Hence, to recap, important topics that we've discussed so far: how do we name hosts on the internet? That's naming. How do we address them? That's the topic of IP addressing. How do we map names to addresses? This is going to be the DNS system. How do we compute those forwarding tables? We're going to have multiple lectures in one project on the routing control plane. And then finally, how do we forward packets? This is the design and implementation of IP forwarding and the IP data plane. And with that, okay, let's pick up again. I've gone slower than I expected, so I might speed up a little bit. Any questions on what we've talked about so far? Okay, so let's switch gears a little bit and let's back up a level. So we've talked about, kind of zooming in packets across links, and we've also talked about a stream of packets or a flow going across a set of links in this network. Backing up a level, though, if you look at the network as a whole and we say, okay, I have one flow going through this network and I have another one and yet another one, inherently what this is telling us is that we have a number of packets or flows that are sharing this network. What I mean by that is they're sharing these links and switch resources. And in particular, when we talk about sharing, we tend to talk about sharing a link or sharing the bandwidth on that link. Okay? And so a fundamental fact about networks, that is what we're going to talk about next, is the fact that network resources are shared. A network has to support simultaneous flows at the same time. Simultaneous users, simultaneous applications, simultaneous flows. And so this question of how do we actually share network resources is very fundamental. Before you even talk about protocols or how you do routing, you have to talk about the model you want to support in terms of how you share network resources across flows or across users. Okay. And if you, if you've taken CS 162, but it's also just a very intuitive idea, what we say when you talk about this notion of sharing resources, what we're really talking about is this term called statistical multiplexing. Statistical multiplexing, how many of you are familiar with the idea or the concept at least? Just show of hands. Okay. So statistical multiplexing is just a fancy term for saying we're going to share resources. Okay. And it's this idea that different users or different people that want to use that resource have a certain demand for that resource. That's how much of the resource they would like to use. That's what we're calling the demand. Okay. And statistical multiplexing is this idea that we're going to combine those demands in order to share resources efficiently. Okay. In contrast to statistical multiplexing as a way of sharing resources is the idea that we would statically partition resources, that there would be no sharing. Okay. So let's take a few examples. Your laptop. If I think of it in terms of users, would you say that your laptop is partitioned in the sense that only one user gets to use it, or is it shared across all users? Yep. What? Oh, okay, that was a one. Yes, it's one user. It is not statistically multiplexed at the level of users, right? One user, one laptop. If you take a server in the cloud, would you say the same? Is it shared or is it statically partitioned? Typically. It's shared, right? So this idea of statistical multiplexing, or having a set of resources and then listening or looking at what the demand for those resources is and accordingly allocating resources, this idea of statistical multiplexing has a very long history in computer science. Right? If you look at within your laptop there and you look at the cores on your laptop, there are a number of processes that are all sharing access to that core. I don't say, oh, only my browser gets to use cores 1 and 2. The file system has to use core 3. That's not how we use it. Instead, we say you have all of these processes, and your operating system scheduler is going to decide which process gets to use which core at what point in time. Okay, that's a form of statistical multiplexing. Cloud computing is a great example of statistical multiplexing. We're going to put together all of these thousands or millions of servers, and then everyone can come and use them, a large number of cloud tenants, as opposed to what actually was a pre-cloud computing era where every company built their own data center. And this idea that you would have a dedicated data center for just your company, made total sense to people pre-cloud computing. I would say statistical multiplexing actually exists in the real world everywhere if you think about it. Your car is probably not statistically multiplexed. Right? It's your car, you own it. A public bus or a flight, an airline jet, is statistically multiplexed. A restaurant, right, you might have a cafeteria in an enterprise that is dedicated to people working at that company. But another restaurant is open to the public and everyone shares using that restaurant. Okay? So that is basically statistical multiplexing. This idea that we're going to have people with their varying demands for resources and we're going to figure out how to share those resources. Why is statistical multiplexing a good idea? Why do we want to statistically multiplex resources? Yep. So it emulates the real world. Why does it work even in the real world? You're right. I'm trying to get at one word. Yep. For saving resources, it is ultimately an efficiency or cost argument, right? We don't each have our own private jet because we can't afford. Some people can, and they have their own private jet. But for most of us, it is much more cost effective to have a jet that we can all share, and you only pay when you need to travel. Yep. I'll get to that in just a minute. Where does the word statistical multiplexing come from? It's actually the next point. Why does statistical multiplexing make sense? Why does it work? Why is it so effective everywhere in life? Right? Yeah, so the word I'm going to pick up on there is expectation. That we expect not everyone needs that resource, a lot of it at exactly the same time. And so let's think about this in terms of bandwidth. So let's say I wake up in the morning, I upload a huge file, then I go have lunch, so I'm not using any bandwidth, then I browse, and then I take the evening off, I wish. So I'm not using any bandwidth. Sean, on the other hand, can't sleep, so he wakes up at 3 in the morning and watches Netflix all night long. Right? And then he sleeps all day. So I maybe needed a gigabit per second in the morning, and then I needed 0 at night. But Sean maybe needs a gigabit per second at night and 0 in the day. So this works out really well. Right? I don't have to build a network that is provisioned for 1 gig for me and 1 gig for Sean. Instead of provisioning a network for 1 gig plus 1 gig, I can say I kind of need 1.2, something closer to 1 gigabit per second. So statistically, that is where the statistical comes in, is that if you take a large number of users or sources that need that resource, and you look at their demand and you say, that demand varies in time. You say statistically, we're not going to need the worst case. Everyone's not going to need the worst case at the same time. Okay, so that's both where the term comes in. It's in expectation. Probabilistically, we don't expect it to happen. And that's true for everything in the real world. Sometimes we all descend on the same restaurant at the same time, but very often we don't. So a little more formally, the reason statistical multiplexing works is that the peak of the aggregate demand is much, much less typically than the aggregate of the peak demands. So what does this mean? Let me break that down. If I took everyone's demand and I added up all the demands at every point in time, so as time is moving along, I say I'm going to take everyone's demand and add it up, then everyone's demand and add it up. And then if I say, okay, for that added up or the combined demand, what was the peak of that combined demand? I'm going to get the peak of the aggregate. Okay, so this was, if you took Sean and my demands at every point in time and you added them up, typically we would be asking, in combination, we would be asking for a little bit over a gigabit per second. On the other hand, I could take Sean's demand and say, what is Sean's peak? It's 1 gig. I could take my demand and say, what is my peak? It's 1 gig. And then I add the peaks. That would be 2 gigabits per second. And typically the peak of the combination or the peak of the aggregates is much less than adding up or aggregating the peaks. Question? How do you know that the resources are shared in a fair manner? Excellent question. You're way ahead. We're going to get to that in many lectures. That's a great question. How do we know that we have all of this demand and we're going to share it in some sensible fashion. And your operating system is your operating system scheduler. It has a policy that says, I'm going to give this process some time and then that process. So we're going to have to develop similar policies and ideas in the networking context. Any other questions? Yep. Yeah, so the question here is, building on the previous question really, do the resources have to be shared fairly? Not necessarily. It depends, it's a question of policy. Some people might want to, some operators would want to share fairly, some might not. And so this is a question we'll get into when we talk about resource allocation. Let me make this a little bit more formal still. So I'm going to say if I have a flow F, I'm going to use P of F to denote its peak for that flow. And so then the peak of an aggregate or a number of flows would be the, say F1 and F2 would be P of F1 plus F2. Okay? So the aggregate of the peaks would be adding up all the peaks. So it would be the sum over each flow of P of F. On the other hand, the peak of the aggregate would just be that I first sum all the flows, and then I take the peak. Okay. And so we say that statistical multiplexing works because typically the aggregate of the peaks is much, much higher than first summing them up and then taking the peak. And in fact, for many real-world distributions, you can show that actually the peak of the aggregate, that means combining all the demands and taking the peak, tends to be much closer to the average. So if you're building a network and you believe this is going to be true, you save significantly on how much bandwidth you have to put in your network. And that's the reason we like statistical multiplexing. Any questions before I move on? This notation, just stare at it for a little bit offline. It's not actually complicated. Really all it's saying is you don't design for the absolute worst case. The worst case is that all of us have our peak demand at the same time. And so instead what statistical multiplexing says is you share resources and you kind of just hope that the peaks don't all occur at the same time. Could this go wrong? Could this kind of premise or assumption bite you? Yep. Network in Berkeley has no excuse. They knew that. See, that was predictable. But you're right. Yeah. So actually, you guys are coming at an interesting distinction, which is, so Berkeley, the start of semester or when we know that the load on the power grid is going to peak, I would have said in those cases, the operators knew that that peak was coming. It was a very conscious decision not to provision for the peak because it's just too expensive. So instead they annoy their customers and turn off your power and you have rolling blackouts and things, or bad Wi-Fi and so on. What about unpredictable? Something goes viral, yeah. So famously in the Bay Area, when there was the last big earthquake, the first thing everyone did was pick up their cell phones and the cell system went down. So this happens. It's very similar to insurance, right? Insurance companies, they give everyone home insurance and then you have wildfires and everyone's claiming their insurance and they never come out of bankruptcy. It's still considered though a very practical choice to make, that this worst case happens rarely enough and the alternative of actually provisioning for that worst case is so expensive that this is what most operators do. Who do you think doesn't do this? Who buys their own jet? The military and the government, for sure. They don't want to take any chances. Anyone else? Yep. The super wealthy, which in the internet context would be the financial exchanges and so on. Right? So the financial exchanges are not, for example, so far, though there's talk about it, they don't run on the cloud and they build their own networks because it's just worth it to them. The loss is too high. So we're going to do statistical multiplexing. Hopefully we have all agreed this is a good way to go. How are we going to do it? And I want to point out something which is a hint maybe, but something about statistical multiplexing that was kind of buried in all of those examples, but I want to call it out explicitly. So and this is the idea that when we talk about statistical multiplexing, the question really is at what granularity are we statistically multiplexing things? So for example, I said your laptop is not statistically multiplexed because you're the only user. What that means is actually at the granularity of users, it is not statistically multiplexed. But if you look at your laptop, at the granularity of processes or applications, it is statistically multiplexed. Right? If you're running too many applications, more than you have cores, your laptop slows down. Those applications are sharing the cores inside your laptop. Right? And so there's actually a question when we talk about statistical multiplexing about at what granularity are we talking about sharing. The same in the cloud. You can go and book a server to yourself, and then you're not sharing it. When you let it go, then that server gets shared again. And so there's always this question of at what granularity are we talking about sharing. So with that, how would you share network resources? Or how would you think about sharing resources? I'm now talking about almost like a mechanism. How would we go about sharing it? Think about the real world. Public transport, restaurants, cloud computing. Right. A quota, when would you get your quota? Would you just always have it? Because then when... You're getting at something. So let me play that back to tell me if I got it right, which is I have a quota, this is how much I want, and I go and I try to book it, in a sense. And if the network has resources, it gives it to me. And then I own that quota. And if not, then I can't use it. Okay, excellent. I'm going to call that a system called reservations. I can reserve resources. Right? Just like a restaurant, you can call and say, I'd like a reservation, or plain. Or what's the alternative? Yep. First come, first serve, which is you just turn up, and you hope that you get the resources. That's by and large the two broad categories or approaches to sharing that we see, both on the internet but also in the discussion about how one should share resources more generally. One is this idea of reservation, that an end host or a user is going to explicitly reserve bandwidth when they need it. Okay, so when you need bandwidth, you go to the network and you say, I would like to reserve 1 megabit per second. A very natural time scale at which to do this, or at which most people who've tried to do this approach, is that when I have a flow of data, when I have some data to send, I'm going to say, hey, can I reserve some bandwidth? Then I'm going to actually send data over that reservation, and then I'm going to say, I'm done. My reservation is over, you can take it back. You can take the resources back. And the other approach is what we've called previously best effort, right? Which is you just send data packets, and it's up to the network to try and get it across. And if they can't, because there were no resources left, they're going to drop a packet, but they're going to try to send it along its way. Okay, so there's reservations and best effort. When we talk about how would you actually implement reservations and best effort, best effort, how you implement it is this packet switching we've been talking about. I send a packet into the network, the switch receives packets. If it has capacity on its outgoing link, it sends it. Otherwise, it's going to drop it. That's best effort. It's pretty straightforward. We'll get to that in a bit. For the rest of this time, I wanted to give a little preview on reservations and how would you do it. So let's set the problem up. I have this network here, and I think we're only going to get to the broad approach, and then we'll do a deep dive on it in the next lecture. But so here I have a topology, and I have these two blue end hosts that want to communicate. Okay. The network has run a routing algorithm and has decided that it likes this red path connecting those two end hosts. Okay. So the network has done its job, it has a path. How would you now implement reservations? So the blue hosts now want to reserve bandwidth along this path. So notice I'm not saying that the reservation gets to pick what path. That was already decided by the network. The job of the reservation is just to book bandwidth along that path. How would you implement this? Yeah. Yeah. So you could send, and that's exactly what many of these protocols or these ideas have tried to do. You could send something that looks like a reservation packet, a request to reserve resources, or what we call a reservation request, through the network saying, for example, hey, can you give me 10 megabits per second? Can you give me 10? Can you give me 10? That reservation request will travel through the path, trying to book 10 megabits per second at every step. If all the switches say yes, then you have your reservation. Or in the terminology that's used, we say you've established a circuit. Okay? So a circuit means that you have successfully gotten your reservation. You've booked resources at every hop along the path. Where did the term circuit come from? It actually comes from the phone network. This is how the phone network worked. Right? When you picked up your phone in the old-fashioned phone network and you got a dial tone, and you dialed your number, and then it would send a reservation request. It would try to set up a call through the phone network to the receiver. And if you were successful, then you had a telephone circuit, and you could talk over that circuit. Okay? So at this point, you would say you've established a circuit. You can then start sending data over that circuit, up to your quota of 10 megabits per second. And when you're done, you've sent the file, you're done with your communication, then you send a teardown message back through the network. Okay. So you'd say, I'm done, I'm done, I'm done, I'm done, and then the circuit disappears. And now those resources that you had reserved are available to be used by someone else. Let's contrast that with packet switching. So in packet switching, I have this packet. In packet switching, every switch is going to process a packet independently. And it's going to process a packet independently along two dimensions. One is each switch is going to treat that packet independently. So this first hop here takes the packet, sends it on. The second hop takes the packet, sends it on. The third hop, and so on. Each switch doesn't care that previous switches have actually processed that packet or they accepted to serve that packet. Each switch is going to independently say, am I willing to forward this packet or not? It's also independent in the sense that it's independent across packets. It's going to revisit that best effort decision every packet it gets. So it doesn't care that I sent the first 9 packets in this flow, I ought to send the 10th packet. It doesn't make any of those decisions. It's truly independent per switch, per packet. So one last point that I want to emphasize here is that both approaches actually embody statistical multiplexing. They're just different ways of supporting or implementing statistical multiplexing that have very different trade-offs. So circuit switching, we're statistically multiplexing across the flows currently in the system. So every flow has a demand. It says this is how much this flow needs. And then it books those resources for the duration of that flow. Okay? So I'm taking the peak. So if I had a particular flow and it was very choppy, let's say 10 gigabits and then 1 gigabit and then 10 gigabit, I'm going to say I'm going to book 10 gigabits for the duration of that flow. But once I don't have that flow anymore, I'm going to give those resources back. So it's not like I booked that quota forever. I wasn't just holding on to those resources forever. On the other hand, with packet switching, resources are given out on a packet-by-packet basis, and you never reserve resources. So you never actually say, I have 10 megabits per second guaranteed for me. You consume the resources for the duration of that packet on the wire, and that's it. So next lecture, we're going to talk at length about which one is better, and we're going to do a detailed design analysis of when or why is circuit switching better, when or why is packet switching better. We're going to talk about different metrics by which we should evaluate them. What I want to pause here for now is just to make sure you understood what circuit switching is. Not whether it's a good idea, but what is it trying to do? Any questions on what is circuit switching trying to do, or how it works at this high level? Yeah? Yeah, it's a good question. I said I'm going to send a reservation request along the path. And in the example I gave you, I said every switch along the path said, yes, you can have 10 megabits per second. What if there was a switch that didn't have 10 megabits per second? What would then happen, you can think of it for now, is you would decline the reservation. So the switches would return a response saying, sorry, you can't have your 10 megabits per second. What should the end source do then at that point? Yeah? Will it find a different path? You could certainly design a network where the network says, this path didn't work, resend me the reservation request, use something in your packet header to tell me to try a different path. It's plausible. None of the protocols that were designed I know do this. It would be fairly complex. Why would you, how could the source actually say, I want to use this path versus a different path? Yep. You could try asking again. for the source to have to pick, just to answer my own question, if for the source to have to pick a different path, the source would have to have some control over how packets are forwarded through the network, which so far, at least in all our discussion, we've been saying the network decides paths, not the sources. Right? The routing algorithms are run by the network. So it would be a fairly big leap to allow end hosts to say how their packets should be routed over the internet. Operators, that would probably make them very nervous. It's a reasonable idea, but one that has a lot of implications. I'm going to pause here, think about circuit switching and whether you like it. We'll talk about why you should or shouldn't like it in our next lecture. Thank you.